Hi guys, so in this video I wanted to explain how any visual field loss can translate to a particular lesion in the visual pathway. So that could be in the brain, or it could be the optic nerve or the optic tract. What I'm going to do first is go through the optic pathway briefly, just to recap from the last slide. So you can just orientate yourself with this image. So it does look a bit busy to start with, but actually it's not that bad, and when you break it down, it does make a lot of sense. So we have two visual fields. So we have our right field and our left field. Right field corresponds to the right eye, left field to the left eye. That's fine. So the right field, let's take the right field for example. So the right field is what you see. So it can be divided into four quadrants. So the right field, left upper quadrant, right upper quadrant, left, right lower, and left lower. And the same for the left field as well. Now let's recap the visual pathway. So the visual pathway starts at the retina, where the retinal ganglion cells, the axons converge at the optic disc, and they form the optic nerve. So they then travel as the optic nerve in the optic canal, and that's in the bony orbit of the sphenoid bone, and they meet at the optic chiasm here. So this is where the nasal fibers from each retina, they cross over, just the nasal fibers, i.e. the nasal half here. The temporal fibers from each retina, they remain ipsilateral, they remain on the same side. You can see here as I'm tracing. So at the optic chiasm, you've got the decussation of the nasal fibers, and then from there they form two optic tracts. And these optic tracts go to their respective hemispheres, and they synapse at the lateral genicular nucleus, which you've got two in the thalamus, so the right and left. So there's a synapse formed here, and these divide into the upper and lower optic radiations, and finally end in the visual cortex. So that's the overview of the optic pathway. So let me explain how we actually interpret what we see in our vision and how that relates to the back of the retina. So for example, if we were to, let's take the right visual field. So in the right field, so let your right eye, right visual field, let's take the right upper quadrant here, as I'm tracing with my pointer, the right upper quadrant here. So that's what we see. Now, if we imagine where are those light rays, where are they going to hit on the retina? When we think about the path of light, so actually they're coming from the top right-hand corner of your field here. They're actually going to hit the bottom left corner of your right visual field on the retina. Bottom, they're going to hit the bottom left corner of your retina, because that's the path of light that's going to be. It's going from your top right corner of your vision, and it's going to hit the bottom left corner of your right eye retina. And we can use another example. Let's use the left upper quadrant of your right field. So that visual field is in your left upper quadrant, and actually the light rays from there are going to cross into the right bottom corner of your right retina. So it's a mirror image. So what you see, the image is actually flipped onto your retina. So I'll give you another example. Let's take the left view. Let's take the left upper quadrant here. So that's what you see, and the light rays from that area hit the opposite side. So now those light rays hit the bottom right corner of your left eye retina. So the image is flipped. Okay. And let's have a look at, let's trace the actual pathway now. So the optic radiations in particular, let me just explain those now. So we know from the optic tracts here that the nasal fibers have crossed over from the other eye, and we've got the ipsilateral temporal fibers from the same side eye. Now those further split into the optic radiations. Now the thing to note here is that there are two optic radiation divisions. So there's the upper optic radiation here, and there's the lower optic radiation, also known as Mayer's loop, but you don't really need to know that. So the upper optic radiations always correspond to the upper half of the retina. So the upper optic radiations always trace back to the upper half of the retina. Those fibers come from the upper half of the retina. The lower optic radiation always translates back to the lower half of the retina. And we can trace that back. Let's look at the green line here. So this is the upper optic radiation. These fibers have come from this fiber in this case has come from the ipsilateral side. So it's come from the temporal. It's a temporal fiber from the same side, and there it hits the upper. That quadrant is in the upper half of the retina. And the orange. So again, this is upper optic radiation, but these are nasal fibers, so these have crossed over, and these are from the other eye. But again, they have come from the upper half of the retina. And when we think about the upper and lower optic radiations, think anatomically in terms of the brain. Well, the upper optic radiations are in the parietal lobe. Lower optic radiations is the temporal lobe, and I'll put a P and T here just to mark it up. So that's where, in terms of the brain, the parietal and temporal lobes are involved. Now let's think about the visual field loss. So let's say we have a lesion here. So that's cut off. So that is, first of all, where is the lesion? Well, it's in the optic nerve because it's before the optic chiasm. And it's taken out both the temporal fibers and the nasal fibers of that same eye. So that is going to simply correspond to a total visual field loss there on the same side. Same thing on the other side. So say if we were to have a lesion here, that's taken out both the nasal fibers and the temporal fibers of that same side eye. So that is going to correspond to a total visual field loss in that right eye. Okay. Now, what would happen if we had a lesion here? So an optic tract lesion. Well, we can trace back the fibers again. Now, so where is the lesion first of all? Well, it's in the left optic tract because it's after the optic chiasm. Now, the optic tract will have two sets of fibers from the ipsilateral. They will have two sets of temporal fibers from the ipsilateral eye, and they have two sets of fibers from the contralateral, two sets of nasal fibers from the contralateral eye, and we can trace those back. So the yellow and the green fibers here, these are temporal fibers from the ipsilateral eye. So the green fibers here and the yellow fibers here. And because at the optic tract, there hasn't been any more splitting into the optic radiations, it's just the whole of that half of the temporal retina is affected. Now, what kind of field does that correspond to? Well, let's take the top left quarter of the retina here. Now, remember, where are the light rays coming from? Well, it's a mirror image, so it's a mirror image, so it's flipped. So the light rays will be coming from the right lower quadrant of the left field, and therefore there'll be a visual field loss here. And what about the other set of temporal fibers? Well, these affect the lower left quadrants of the retina. And where are the light rays coming from? Well, they're going to be, it's a mirror image again, so it's going to be from the right upper quadrant of the left visual field. So we've done the temporal fibers. Now we need to do the nasal fibers that have crossed over from the other eye. So that corresponds to the dark blue and the brown. So we can trace them here. So the brown fibers have crossed over, and there's one set of fibers that have come from the top left-hand corner of the retina and from the bottom left-hand corner of the retina. And these equally correspond to visual field loss, like so, because it's a mirror image that is reflected on the back of the eye. So this is what's called a homonymous hemianopia. And because the lesion is in the left optic tract, we call it translates to a right-sided homonymous hemianopia. And the reverse will be true for the other side. So if we had a lesion here, then we can trace back the fibers again. So we have two sets of nasal fibers that are affected from contralateral eye, that come from the contralateral eye, and two sets of temporal fibers that have come from the ipsilateral eye retina. And these would translate to this source of field loss. The same type of field loss, just on the opposite side. Well, let's try and go further back. I'll rub that P there. So how about if we had a lesion right here? How would that translate into a field loss? Well, where is the lesion, first of all? It's in the left upper optic radiation. And which lobe of the brain is that? That's in the parietal lobe. Now, what do we know about the upper optic radiation? We know that the nerve fibers from the upper optic radiation have come from the quadrants in the upper half of the retinas. So let's trace the green. There's going to be one set of fibers from the temporal side, and there's going to be one set of fibers that have crossed over, i.e. nasal fibers from the contralateral eye. So the green are fibers, they are ipsilateral temporal fibers, and they correspond to this quadrant here. And look, this green quadrant on the retina itself is in the top half of the retina because it's come from the upper optic radiation. And what kind of field loss is that going to contribute to? Well, let's remember the mirror image. The light rays have come from here. And that the light rays from this right lower quadrant are projected onto that quarter of the retina. And therefore that path is affected. So we've done the temporal fiber from the ipsilateral eye. Now what about the nasal fiber from the contralateral eye? Well, that's the brown root. So again, up optic radiation. So we're expecting that a quarter of the retina in the top half of it is affected, and that's true here. We can trace it back. So this brown quarter on the retina, that is in the top half of the retina because it's come from the upper optic radiation. And what about the visual field loss? Well, think of the mirror image again. It's going to be flipped. So that's called an inferior quadrantenopia. And to be specific, because the lesion is in the left side, it's going to be a right inferior quadrantenopia. And that's indicating a lesion in the parietal lobe. Let's do another example. Let's try. What about if there was a lesion here? So let's think, where is the lesion? Well, it's in the temporal lobe on the right side of the brain. It's in the lower optic radiation. So what does that mean? That means that the nerve fibers in the lower optic radiation have come from quadrants on the lower half of the retina, wherever they may be. There is one set of fibers from the ipsilateral side, i.e. the temporal fibers from the same side eye, and there's a set of fibers that have crossed over from the other eye, the nasal fibers of that eye. So let's trace them back. So the red roots, these are the nasal fibers from the contralateral eye. And we know that the quadrant in question on the retina is going to be in the lower half of it. because the fibers have come from the lower optic radiation. And how is that going to translate to a visual field loss? Well, it's going to be the mirror image again. So this would be affected. The other set of fibers, the pink, these are the other set of fibers must be therefore the ipsilateral, must be fibers from the ipsilateral side, i.e. the temporal fibers of that ipsilateral eye. We can trace them back. So these haven't crossed over. And we know that the quadrant in question is going to be in the lower half of the retina because they've come from the lower optic radiation. What about the visual field loss? Well, think of the mirror image again. So it's going to be a loss in this quadrant because that's where the light rays have come from. And they project onto this quarter of the retina. And this type of visual field loss is a superior quadrantenopia. To be specific, it's a left-sided quadrantenopia. A left superior quadrantenopia, because there is a lesion in the right side of the brain, the right temporal lobe. An easy way to remember all this is to use an acronym called, we go by PITS. If you remember PITS, this will be really easy. So PITS stands for parietal inferior temporal, can't spell temporal, still can't spell temporal, temporal to superior. So let me explain that. So that means a lesion in the parietal lobe will lead to an inferior quadrantenopia. A lesion in the temporal lobe will lead to a superior quadrantenopia. And depending on which side, it will be the opposite. So for example, if I have this kind of visual field loss right here, in a question they may give you that, they may ask you where the lesion might be. So to describe this kind of field loss, we would say it's a left-sided superior quadrantenopia. So superior, that means there's a lesion in the temporal lobe, and because it's on the left side, that means the actual lesion itself must be in the right temporal lobe. And that's true because we can see here, the red and the pink lines, this is in the right temporal lobe, and that corresponds to that kind of field loss. Try another one. Let's do this kind of field loss here. So how would we describe this? We would call it a right-sided inferior quadrantenopia. So inferior, from PITS, that means that there's a lesion in the parietal lobe, and because it's a right-sided quadrantenopia, we know that the lesion is in the left parietal lobe, and we can see that here. So these are the green and brown quadrants here, and this translates to these fibers here, the upper optic radiation, i.e. in the left parietal lobe. So if you remember PITS, it becomes really easy to remember quadrantenopias. And I hope that helps sort of seeing it anatomically and mapping a lesion anywhere in the optic nerve, optic tract, or in the radiations to visual field losses. Hope that helps.